Oh, welcome back to Sunday Science, everyone. Glad you could join us. So, if you've been watching for the last month or so, we've obviously been dealing with a great deal of spectroscopy, how it is that it works, why it is that it works, experiments you can do at home in order to sit down and have fun, and also potentially cause some carnage, which is not actually the goal, but sometimes it happens. So last week we had a...
Do you hear me?
Yep, Tornado, you are in.
You're in.
Cool.
We're live. Welcome.
Thank you.
Carry on, Andy.
All right. So last week we had a little brief demonstration of the burner unit. I was intending to have the homemade spectrometer set up so that on burn test number 2 we could run that. I've been having some issues with my helmet camera and it didn't wind up working. I did run another burn test, which was well, it was pretty interesting. I haven't actually got it completely compiled into a video yet, but I suppose we could show that real quick so that we can get on to the remainder of the reason why we've been diving into this subject pretty hard as of late. There's some pretty awesome stuff happening down in the Atacama Desert right now, so this well, spectroscopy plays into all of it in a very, very awesome way. So, oh, heck, why don't I go ahead and show the insanity of last night real fast, if you don't mind.
Hold on, I gotta switch gears. Here we go.
I know. I'm just gonna present for just a moment.
Make my life fun, not a problem. Gotta keep me on my toes and whatnot. Okay.
All right.
Screen is yours.
Maximize this out. Okay, hopefully that's being seen the way it kind of should be.
Yeah, I'm seeing it.
I'm seeing it fine.
All right. So burn test number 2 saw a little modification to the entire device. Things started getting a little out of hand, though. It appears that I have some significant leak issues that need to be resolved. But nonetheless, it was still fun. Yep, you can see the leakage now. And it only gets worse.
Tell us you still have eyebrows. That's all we really want to know.
I have all my eyebrows and all the fur on my knuckles that I used to.
Okay. All right. We are relieved.
There it goes. It was a little exciting and overwhelming at first, but eventually the leaks did seal up after I lit myself on fire a couple of times, but...
Indeed. And for anyone watching or anyone watching in the future, knowing you, I'm fairly convinced there was a fire extinguisher close at hand for if things got completely out of your control, correct?
There was a fire extinguisher about 4 feet away from me.
I'd see. I didn't even need to ask that.
A little bit too much oxygen, obviously. The air supply has definitely gotten better, but now I need some sort of agitator to stir the chemicals around a little better.
Have you considered gas feed instead of liquid feed? Just to make your life a little more complicated.
And yet I lit myself on fire again.
Oh, lovely.
So, yes, but doing spectroscopy is a tremendous amount of fun. It is an amazing science that you can learn a lot from, but it's also kind of dangerous if you're being an idiot like I was last night.
Whoops.
Okay, good safety tip. Don't be an idiot.
And always have a fire extinguisher handy.
Absolutely.
Of course.
And the magnesium, obviously, once it ignites, it has a tendency to just melt the aluminum and kind of smolder and... Yeah.
Yeah. Magnesium is fun like that.
It burns
Indeed.
hot.
So that's pretty much that. thought I'd just share that real quick. Burn test number 2 did not need a spectrometer involved. It would have probably just been a disaster, as the majority of the burn test was. So we'll keep going with that experiment and toying around with different ideas that we could hopefully make work. But in the meantime, big reason why I've been bringing all of these kind of things together with the Space Observatories series, with spectroscopy. Obviously, one of the most awesome telescopes in the Space Observatories I intentionally left out because I was waiting for an episode, well, just like this one, to bring it up. Kepler. And everything that is happening with exoplanet research right now is absolutely phenomenal. And Kepler, if you're into science, you darn well know what's been going on with the discoveries of exoplanets, and obviously the TRAPPIST-1 system being a huge hit. Not necessarily saying that there's confirmed life anywhere else in the universe, but it's still pretty awesome. So I figured a little short vid about how it is that Kepler actually does its work would be in order today. If you wouldn't mind firing that up for us, Si.
Not at all. Not at all. Here it comes.
We have an innate curiosity about our origins. Is life in our galaxy common? Does it exist? Are we alone? How unique is life here on Earth? The Kepler mission is one step in answering that question.
Kepler mission is a huge step forward in answering the question, what is our place in the universe?
The Kepler mission is NASA's first mission capable of finding Earth-like planets orbiting other stars in the galaxy in a region around the star we call the habitable zone.
The habitable zone is where we think water will be. If you can find liquid water on the surface, we think we may very well find life there. So that zone is not too close to the star because it's too hot and the water boils, not too far away where the water is condensed and the ice covered, planet covered with glaciers. It's the Goldilocks zone. Not too hot, not too cold, just right for life.
The primary science goal of Kepler is to answer the question if Earth-like planets in our galaxy are common or rare. Kepler is going to detect planets via the transit method. What we aim to do is to measure the brightnesses of stars very, very accurately for a very long period of time without blinking, so that when the planet passes in front of the star, the light output from the star is going to dim just a little bit. That star is going to blink for about 12 hours, and we will be able to measure that dip in brightness. And it's that dip that we call a transit.
Kepler is a different animal from the Hubble Space Telescope or the Spitzer Infrared Telescope because it doesn't take pictures. You won't see beautiful images that you see from Hubble because we're not doing that kind of science. Those types of missions like Hubble and Spitzer are designed to focus on specific targets.
If you hold your hand at arm's length with a grain of salt or a grain of sand, that's about how much of the sky you can see with a normal astronomical telescope at any one time.
Kepler has a field of view that's 10 degrees by 10 degrees.
Our field of view is about as big as your hand at arm's length covering the sky.
So rather than taking pictures of very concentrated parts of the sky, we're looking at taking a very broad snapshot of a lot of stars.
Kepler takes really fuzzy pictures, but the thing that Kepler is designed to do, and it does very well, is look for very small variations in the brightness of the stars.
An Earth-like planet passing in front of a Sun-like star is going to cause the brightness of that star to dim by only 1 part per 10,000. That's like looking at a headlight from a great distance and trying to sense the brightness change when a flea crawls across the surface. But the Kepler instrument is designed to detect such small changes in brightness.
The Kepler sensors are CCDs. The CCD in your camera is about the size of one of your small fingernails. The CCD chips on Kepler are a couple of inches square in pairs, and there's 42 of those. In your camera, you might have a few megapixels. If you have a really nice camera, you might have 10 megapixels.
We have 96 million pixels, and they have very low noise, so we can find very small planets.
Once Kepler is launched from the Earth, it will go into what's called an Earth-trailing orbit. Astronomers call that a heliocentric orbit, which means sun-centered orbit.
It looks at the stars continuously, day and night, 365 days a year, and it slowly moves away from the Earth, orbiting the sun by itself.
And from there, it will point itself at the Kepler field and stare at the Kepler field nearly without blinking for 3.5 years at least, maybe longer if we have an extended mission.
Kepler will be looking in a region of the sky that you'll see almost every night in the summertime.
The field of view is kind of nestled underneath the wing of Cygnus the Swan, between Cygnus and Lyra. Now, in that area of sky, there are something like 6.5 million stars. Why do we need so many?
Because of the way Kepler looks for planets, we have to have planetary systems that are lined up so that the planet actually passes between the star and Kepler telescope in its orbit.
The probability of that happening if you just throw stars randomly down in our galaxy is something like 1 to 10%. It's small. So of those 6.5 million scattered over that 100 square degrees, only maybe 200,000 are interesting to us.
We select the 170,000 or so that are most suitable to look at for planets with the Kepler telescope. Finally, we expect to end up with somewhere between a few hundred and a few thousand signals that are really planets around the stars that we're looking at.
Well, this is the
If only
first
they
time
knew what they
that
would wind up seeing.
photometry, the measurement of the brightness of stars, will ever be done at this level of precision. And it will be done simultaneously on more than 100,000 stars continuously over a period of years.
We're somewhat like pioneers, very much like the explorers that were looking for new lands to settle. And that's how I see what we're doing. We're looking in this region of our galaxy for other habitable worlds.
I think people everywhere want to know whether with all the stars out there, do they have planets that are Earth-sized? Are Earths frequent or are they rare? And this gives us that answer. It's the next step in mankind's exploration of the galaxy.
There's two extreme answers that Kepler might give us. It might tell us that there's an Earth-like planet practically around every star we look at. Imagine the possibilities for life in the galaxy or life in the universe.
If, on the other hand, we found out that Earth was very special and that the typical star, like the Sun, is not hosting planets like the Earth, I think that would be a real surprise as well and would really make us reconsider the special nature of Earth.
We are now finally at the point where our technology allows us to build a machine that can make the observations to scientifically answer this question.
How many stars like the Sun did develop planets around them like the Earth? I think that's such an important question to everyone and so interesting that we really have to do it, and it's a once-in-a-lifetime opportunity right now.
Awesome.
Indeed.
I thought that was a pretty good one to sum up how it sum up Kepler in what was that, like 7 minutes? So it's really fun the way that Kepler does actually sit down and hunt for exoplanets so that ground-based observatories can then sit down and pinpoint the stars that it's noticed, regular dips in brightness, and start doing other sorts of analysis so that we can determine, is this an exoplanet? Is this, some gravitational lensing effect that maybe we were not aware of taking place in that region? Is
it a Dyson sphere?
Yeah, right. Oh, was that Bjorn star or whatever?
All right. Yeah. Okay.
But yeah, there's
ruled out. Ruled out. There's no Dyson sphere.
not yet. Maybe there is on a distant side of the universe that light can't reach us from and never will be able to reach us from, but that's just a question we're always going to have to ask until we finally discover one or build one ourselves.
Indeed.
So obviously that's, it's pretty obvious the methodology used with the Kepler Space Telescope to sit down and hunt for exoplanets. My dogs have been going ape all day, so sorry if you wind up hearing them in the background. There's no stopping them for some reason.
Dogs are always welcome here.
Right. Life without dogs would be a boring one. Anywho, so the discrete and very subtle drops in light from a star, being able to determine there's an exoplanet there. There's also other methods utilized, such as physically seeing if the star itself wobbles due to the gravitational tug from another planet. I think it was around 1995 was one of the first confirmed exoplanet discoveries. And it was from the gravitational tug-of-war, actually, not the dimming of light. To my knowledge, we didn't have sensors capable of detecting that in 1995, but we absolutely could watch the physical wobble of a star, and that's just cool to sit down and be able to observe an object long enough to notice, hey, there's a little wobble happening here. Why? And more questions, and of course, more science.
Something Chisholm seems to not believe in.
Well, that is true. He does have a difficult time with that. So obviously, with the last several episodes being about spectroscopy, how it is that we can determine what an element is based upon its absorption lines, how we can determine the chemical makeup of other stars in our local group and in other galaxies. All of these things tie into a new device and a new tool, and one of the most sensitive of its kind that have ever come into existence yet. And ESO's EELT in the Atacama Desert in Chile, only 3 or 4 days ago, I think it was on the 6th of December, actually, it finally made its first light. And, well, not the EELT, but this particular tool, or instrument, I should say, known as Espresso. I can't remember exactly what the acronym stands for. It was a little...
Clearly it stands for coffee.
Oh, of course. It's very, very clearly coffee. But as much as I do love coffee, and actually wouldn't mind a
if memory serves me, if memory serves me correctly, and this is purely from memory, it's the Echelle spectrograph for rocky exoplanet and stable spectroscopic observations. You understand that's purely from memory, I'm telling you that, right?
Absolutely, of course.
Okay, I don't think anybody believes that, but anyway.
Yeah, so the Espresso instrument went online and did its first light. I'm not sure exactly which system it did perform its first light test on. However, this tool is very unique. Bubble in my throat. This tool is very unique in the manner in which it's being utilized for exoplanet research. And instead of sitting down and watching for that shift in brightness or that signature wobble of a star, clearly the smaller the object orbiting the planet or orbiting the star, it's going to produce a significantly less dip in brightness than a large, say, Jupiter-sized planet. So it's easy to detect Jupiter-sized and larger planets, and with everything that we've been discussing, it's easy to see why. Smaller, rocky, potentially terrestrial planets, are terrestrial-like planets, are much more difficult to see. So, utilizing new technology and the most sensitive spectrograph that has ever been produced to date, we're now able to utilize different methods to detect small rocky planets around neighboring stars. And that's part of the reason why I've been doing the spectroscopy, aside from the fact that it's really fun to set all of that up. It's also leading into, well, let's go ahead and let the experts at ESO sit down and tell you all about their new fun instrument, because it's the next couple of years of observations that it's going to make are going to be absolutely phenomenal. So, if you wouldn't mind, Si, go ahead and...
Not a problem.
From memory.
Okay, you want me to type in binary the video from memory,
yes.
So that you all can watch? Happy to do so. Hey, Steve's here too. Hi, Steve. Okay.
Oh, hey, Steve.
Here it comes.
I suppose if we don't want to deal with typing in the actual binary code, we can just go ahead and play the video.
All right, I'll do that. It'll be quicker. Here we go.
All right.
Hello and welcome to Space, here from the Observatory of Geneva, home to experts in exoplanets, the name given to planets outside our solar system. So far, they've managed to find 3,559 of them, but they believe there could be literally billions of them across the Milky Way. Let's find out more. The first exoplanet to be discovered looks rather like this. What's known as a hot Jupiter, a giant gas planet orbiting close to its star. That discovery, made by University of Geneva professor Michel Mayor in 1995, kick-started a revolution in astronomy. A revolution that's taken us from one confirmed exoplanet to thousands.
It's amazing. It's incredible. That in 20-odd years, we've gone from a dream, are there planets around other stars, to the discovery of such a large number.
Over the past 2 decades, research has focused on hunting smaller planets like our own.
Nowadays, people are excited about more specific things. Finding habitable planets, rocky planets like Earth, at a distance from their star, that means liquid water can exist there.
The vast majority of exoplanets can't be observed directly because they're far too dim to see compared to the bright stars they orbit. So scientists have developed 2 key techniques to detect these distant objects, as exoplanet expert David Ehrenreich explains.
So we're going to do a little simulation to explain how we detect planets. So I've got 2 snowballs. The small one will serve as a giant planet, like Jupiter, a gas giant, and this is its star, a bit smaller than our Sun. The method that we developed here, because we can't observe the planet directly, consists of observing the movement of the star as it's affected by the planet moving around it, and that gives us the mass of the planet. Then, in certain situations, we're lucky and we see the planet pass in front of the star, and that's what we call a transit, a tiny eclipse. And that shows us the size of the planet, and that's what we're going to measure from space with the Cheops mission. Sometimes the planet and the star get away.
This is Cheops, an ESA satellite currently being built and due for launch next year. In space, it will be able to measure the radii of exoplanets with unprecedented precision. That data will then be paired with ground observations from ESO's VLT telescope in Chile to seek out rocky planets like Earth. And in spring this year, the VLT's exoplanet hunting abilities will be boosted by a brand new instrument called Espresso.
Welcome to the clean room at the Observatory of Geneva, which is home at the moment to the Espresso spectrograph. Espresso is everything you can see here, with the instrument inside this vacuum chamber. The light comes through here, through this device. It's collected and sent into a tiny optical fiber the width of a human hair. This optical fiber takes the light here up to the spectrograph. And there we take the light and we spread it out into its different colors. That's what a spectrograph does, in order to analyze the spectrum and determine the speed of the stars. It's really the best spectrograph we can make today. It's the Ferrari of spectrographs. And it's with that we'll search for habitable Earth-like planets, we hope.
It's thanks to innovations like Cheops and Espresso that the field of exoplanet research can expect to accelerate its rate of discovery even further. So will we find another planet like our own, rocky with liquid water and a breathable atmosphere? It's an epic scientific challenge, but British astrophysicist Carol Haswell is optimistic.
The dip that would be caused by the Earth transiting across the Sun is 1/100th of 1%. So if you think about that, we need to measure the brightness of a star to a stability of 1/100th of 1% over a time span of 3 years. So that's not a trivial thing to do. And I think it's going to turn out that that habitable planets with liquid water on the surface that we could potentially walk around on are going to turn out to be plentiful.
Hunting those Earth-like exoplanets demands extreme precision, but the scientific rewards on offer mean the pioneers are now joined by scores of new researchers.
That number didn't get there by itself. It means that a lot of people are working in this field. An old dream of humanity is now a skyrocketing sector of science.
From hot Jupiters to frozen ice planets, it's projected our Milky Way is home to over 1 billion exoplanets. The hunt is on to find them. That's all from us here at the Observatory of Geneva. You can keep up to date with other news from the universe on our space blog on Euronews.com.
So basically, from what I hear, they're saying that finding an Earth-like planet is almost inevitable.
Well, it certainly sounds like they're putting their best effort into doing it, doesn't it?
Yes, it does.
Wait.
Oh, you know, I can't argue with their tactics on that one.
Indeed. And let's see. Yes, Emma, he did say espresso.
Indeed. I also made a mistake earlier, and I'm so excited for the EELT that I said EELT. Obviously, the thing hasn't been built yet. I was talking about the VLT. VLT is actually a grouping of 4 different telescopes, but you know, mistakes are made. It happens, especially when it's all acronyms.
It may not have been a mistake. Steve and I were talking about Gallifrey a little while ago. You know that timey-wimey thing.
Wibbly wobbly, timey-wimey stuff.
Indeed. Anyway, that was a very good Matt Smith there, by the way. Okay, sorry, Andy. I digress.
Oh, no worries. So it's been surprisingly hard to actually gather reliable news sources on Espresso doing its first flight test, but you know, utilizing spectrometry as a means of detecting exoplanets is obviously somewhat new, but not not necessarily, because the Hubble was actually outfitted. Service Mission 4, I believe, it was outfitted with the spectrographic tool as well. So this is something that we've been doing for a little while, but the accuracy and precision of this particular mechanism is absolutely amazing. And like I say, God, my dog's annoying. The results, the data sets that are going to come in from this tool is just mind-boggling to think about. We've heard so much of, okay, like the TRAPPIST-1 system. Hey, there's these tidally locked planets that are around this brown dwarf, and the majority are in the habitable zone, and it's a major discovery because it's kind of one of the first of its kinds. Well, now with these new tools that we're building, and with another that's going to be heading out into space after another delay, hopefully there aren't too many more of those, we're going to be making these discoveries on a weekly basis almost. We live in incredibly exciting times with the technology that we're able to place into our observatories, with adaptive optics and ground-based observatories, with tools like the Espresso. The discoveries are just going to start. They're going to be so paramount, and they're going to happen so fast that we'll almost be inundated with this knowledge of how many other stars do have rocky planets. I can't wait. I think it's absolutely amazing. Obviously, with a lot of the stuff that we've learned from Juno and all of the data that we were able to collect from Cassini, we're well aware of the fact that there is liquid water all over our own solar system. So being able to detect liquid water on exoplanets, we're close. We are very close to being able to take those measurements, and it's just really exciting time in astronomy right now. I feel like there could be more, but go ahead, Tornado.
Emma May is actually bringing science into this, if that's okay, though. She says they're basically taking an occultation approach instead of measuring the Doppler shift in the star so they can get the radius of the exoplanet.
With one method, yes, that's exactly what they're doing. With the spectrograph, they're actually doing, I believe, the exact opposite, and they are actually measuring the Doppler shift. And some of that is going to come in with, oh heck, let's just get it out of the way because I've been wanting to watch this one again for a little while now. So if you would, kind sir, fire up the James Webb Space Telescope.
Alrighty. And here it comes.
Since the first astronomers pointed telescopes at the heavens, they have sought to see more, see farther, see deeper. Space astronomy changed on April 24, 1990, with the launch of the Space Shuttle Discovery, carrying aboard it the Hubble Space Telescope. A lot of people think we launched Hubble into space to put it closer to the stars, but the real reason lies in that old children's song, Twinkle, Twinkle, Little Star. We all know that song, and it describes a very real phenomenon. The Earth's atmosphere both distorts and blocks light coming in from space. In space, beyond the atmosphere, the stars don't twinkle. They shine steady, and that allows you to get the stunning images we've become accustomed to seeing from Hubble. But that wasn't Hubble's only benefit. It's also one of NASA's great observatories. These are general-purpose telescopes designed to be able to observe anything and everything in the cosmos.
I need
there are a lot of observatories in space, but most of them are designed to answer one or two specific questions. Hubble was built to be as inclusive as possible. It was supposed to answer as many questions as you could think to ask, at least as far as its design allowed. And Hubble succeeded splendidly at that. We've seen planet-wide dust storms on Mars. We've seen the astonishingly strong and surprisingly variable auroras of Saturn. we've looked deep into dense star clusters containing tens of thousands to millions of stars. We've examined the birth of these clusters as they emerge from the interstellar clouds. And we've watched stars die, some releasing their outer layers gently into space like smoke rings. Others forming cosmic butterflies. Some expiring in tremendous explosions that blast their material across the cosmos, expanding for tens of thousands of light years until their remnants ultimately fade away. We've explored the varieties of galaxies, some with beautiful spiral shapes, and some with vast ellipsoidal collections of hundreds of billions of stars. And we've seen galaxies in massive clusters of thousands arrayed through space and time. This is perhaps the most important image Hubble has ever taken, the Hubble Ultra Deep Field. It shows us galaxies stretched all the way across the universe, 5, 6, 10 billion light years away. This is light that's taken billions of years to reach us in our corner of the universe. So we see these galaxies not as they are today, but as they were when the light left them, like getting a postcard in the mail that's been traveling for a very, very long time. And in the end, we see nothing. Is that because we've reached the end of the universe? No. What we've reached is the limit of Hubble's vision. As amazing as Hubble has been, we've come up against the immutable reality that Hubble can't, in fact, see everything. To carry us farther, to step beyond Hubble, we need the James Webb Space Telescope. Like Hubble, Webb is a general-purpose observatory. And like Hubble, Webb will orbit in space, giving it the clarity that comes from being beyond Earth's atmosphere. The Webb telescope sees infrared light, which is visible to the human eye, though we still perceive it as heat. Putting an infrared telescope like Webb in space is going to open entirely new regions of the universe to us. To understand this, you need a little astronomical background. You've probably all heard that our universe is expanding. But what you may not know is that as it expands, the light traveling through the universe also gets stretched. So what started out as visible light and ultraviolet light, the two types of light the earliest objects in the universe emitted most strongly, is changed. It's stretched into another wavelength, infrared light. If we want to see the earliest objects in the universe, we have to see that faint infrared glow. So why haven't we done this before? Well, we have. We launched the Spitzer Space Telescope, which isn't as well known as Hubble, but has made incredible discoveries of its own with the infrared capabilities Hubble lacks. But when it comes to resolution, Spitzer's images are a lot more like ground images than they are like Hubble images. To get Hubble quality images in infrared light, we need something more. We need a giant mirror. Spitzer's mirror is just over 2.5 feet across. Hubble's mirror is about 8 feet across, so that's about a bit taller than a human being. And Webb's mirror uses 18 hexagonal mirror segments to create a reflective surface more than 21 feet across, almost 2 stories tall. Clearly that's pretty big. How do we get something that size into space? Obviously we can't ship it like this. The answer is origami. We're going to fold Webb up inside the rocket that launches it into orbit. Once it's in space, it starts to unfold. The massive mirror opens up. Its tennis court-sized sun shield, which will protect it from unwanted infrared emissions from the sun, Earth, and Moon, stretches out. And all this happens while it travels approximately 1 million miles away, to a point farther away from our planet than even the Moon. So, what are we going to get for all this effort? We are going to be able to see past all these galaxies in the Hubble Ultra Deep Field. We're going to be able to see beyond even the most distant red dots in these images, the tiny, newly formed galaxies at the very edges of Hubble's vision. We're going to see the most distant and earliest galaxies in the universe, the first stars and galaxies to form after the Big Bang. We call these objects the universe's first light. Hubble has been able to observe the adult, teenage, and child galaxies of the universe. Webb will see the toddlers and infants, filling in our story of galaxy formation and evolution as surely as adding missing photos into a family album reveals how humans grow and change over time. But this isn't the only area where we know Webb will provide breakthroughs. This is Hubble's image of the Eagle Nebula, the famous Pillars of Creation photo. Inside these pillars of gas and dust, new stars are forming, but we can't see them because the dust blocks visible light. But it doesn't block infrared anywhere near as well. Infrared light can beam through the nebula, and if we can see it, we can see the newly formed stars within. Hubble's view of the Orion Nebula shows hundreds of newborn stars only a couple million years old. But if we zoom in on Spitzer's infrared image, we see thousands more hidden inside. Orion is the place where we get the best view of not just star formation, but also of the new solar systems forming around those stars. We know that planets, new Earths, new Saturns, new Jupiters are forming inside these dark dust rings, what we call interplanetary disks. But we can't see them. They are hidden behind the dust. Webb's infrared vision will allow us to see through these opaque clouds so we can discover how solar systems like our own came into being. We will be able to see what our own solar system would have looked like after the Sun had formed, but before Earth existed. And Webb's vision is going to take us even farther than that, to individual planets beyond our solar system. This isn't one of Hubble's most dazzling images, but it is an important one. Several planets are orbiting around this star, but their light is lost in the bright glare of their sun. If we can remove the star's light, we can see the planets, these bright dots you see here. This is an infrared observation. Planets which don't shine with their own visible light are usually brightest in infrared. The best way to observe planets is with a high-resolution infrared space telescope. But Webb will be able to take even that another step further. Some extrasolar planets, from our point of view, pass in front of their stars. When that happens, some of the star's light passes through the planet's atmosphere. We can analyze that light and measure things about the atmosphere of that distant world. So what does that mean for us? Well, here is the plotted infrared light of 3 different planets. You're seeing the differences in those planets that indicate the presence of carbon dioxide, ozone, and water. These are the telltale differences between Venus, Mars, and Earth. The first signs of life elsewhere in the universe will not be photographs of civilizations or a visit by little green men. It will be features in the atmospheric spectrum of an extrasolar planet that show biological activity. And that's what Webb has the potential to give us, that tremendously exciting discovery. So when is all this going to happen? Webb is scheduled to launch in 2018, just 6 years away. An enormous amount of the work on the telescope has already been completed. All of Webb's 18 mirror segments have been ground, polished, coated, and tested.
This is a slightly
its
older
cameras
video,
and other
obviously,
instruments are nearing completion or in their
awesome.
final stages. But since Webb will be located 1 million miles away, it has to be perfect before it launches. So we're testing everything. The pieces get tested separately, then together, then as part of the actual telescope. They're tested to make sure they work in the extremes of space and that they can survive the violence of launch. When it's time to test them as part of the entire telescope, they're brought to NASA's largest test chamber, this cavern-like thermal vacuum chamber at Johnson Space Center, which is being refitted especially for Webb. If it looks familiar, that's because it's famous for being used to test the Apollo space vehicles. It seems fitting that chamber used to prepare humanity for its first true exposure to the heavens, is also where NASA's next great space observatory is coming together. Every decade, astronomers conduct a survey to determine the astronomy community's top priorities. Webb is their #1 priority. This is the observatory they want above everything else. We've already explored some of the reasons why, but not the most important reason. If Hubble is any guide, Webb's most important contributions to our understanding of the universe will probably surprise us. Because it was designed as a general-purpose observatory, it is extremely versatile. The Webb Space Telescope will be able to answer the questions we have, and then move on to questions that we haven't yet thought to ask. For example, before Hubble, we thought the expansion of the universe was slowing down. But Hubble made crucial discoveries to confirm that actually it's speeding up, and for that to happen, there may exist some form of strange dark energy. This discovery won its scientists the Nobel Prize in Physics this year. The universe doesn't always work the way we think it does. It surprises us again and again. We've only begun to chip away at the mysteries that are out there. And Webb, because it's designed for this purpose, will be able to explore, confirm, or deny these discoveries as they arise. And that is the true power of Webb. Its potential for unbounded discovery, its ability to reveal wonders we didn't even know existed. That capability, perhaps more than anything else, makes Webb the future of space astronomy.
Oh, I can't wait for Webb to launch.
Oh, you're not the only one. I think I mentioned to you before. I was lucky enough to see the little fellow when it was it only had 6 mirrors attached over at Goddard.
That's right. You did say that before.
Indeed.
You know, all of those mirrors were ground right here in Colorado.
Ah.
Yeah.
Then we can count
Ball
on the quality.
Aerospace ground all of them. They're in Boulder, just 30 miles from me.
Very, very, very amazing device, and finely ground mirrors. I'm told they were subjected to severe analysis.
Yes, wouldn't want another spherical aberration debacle like we had with Hubble. That would be pretty terrible at the L2 point.
Indeed, but that is true. The repair mission would be a little more difficult. But
it would be one of the most amazing feats of humankind to actually go out and repair something that was at the L2. It'd almost be more awesome than going to Mars.
Oh, and even better, have them wear cams. That way they can broadcast it live. That way every astronaut there can turn around as it's flying off and say, "Here you go, Flurfers. This should be the final nail in your stupidity coffin."
Well, you'd have to make sure that they were using Vidacon cameras, not digital cameras.
Yes. Did you see MMA's comment? How many times have they gathered together and said, "Ladies and gentlemen, our highest priority this year is proving the Earth round"? Anyway,
oh my gosh!
Absolutely zero.
Yeah, Webb is definitely an interesting critter. Let's see. The adjustable mirror. You see, we can't have a focusing issue because all the mirrors are adjustable after launch. And
indeed, I can't wait for it. It's just going to be so awesome when it launches and starts being in service, and like a kid in a candy store with that.
Yeah, and the plate, the first surface on the mirrors being gold and all, I had always assumed, wow, that must be a heck of a lot of gold. That must be expensive. No, it's about $100. About $100.
Yeah, it's microns thick.
Exactly. It's less than a budget wedding ring, I was told.
Yep, it's vapor. What is it? Vapor deposition.
Yeah, is
absolutely. That's some of the coolest technology I think I've ever seen actually take place, and if you haven't ever watched a video of seeing how a telescope mirror gets its coating or gets recoded, I suggest taking a look because that is just too cool.
Yes, it is.
Maybe in a future episode we will we did segments on telescope technology. Maybe that would be an interesting one for at some point in the future as well.
Absolutely, definitely could. That's a really good idea. And Emma, wouldn't surprise me if it was able to get to Antarctica at the same rate of speed that it would get to North America.
299 point something thousand kilometers a second.
I find myself wondering if Andy, seeing the word Antarctica, is getting all happy again.
A little bit. Yep. Again, didn't mean to pirate half of movie night while I was in on it, but
do you think any of us were displeased hearing such news, Andy? And in case anybody watching now or in the future is unaware, why don't you say it again?
I was going to try and resist, but
don't resist.
Yeah.
You opened the floodgates.
We're happy.
Frontline may be getting deployed to Antarctica in August. As I said on movie night, I still do have another round of interviews, and if somebody else beats me, then they beat me, but there's a very good chance I might be able to go and have a deployment. If I get too excited again, I'm just going to wreck up my own show. So I already wrecked up yours by going off on a tangent.
Save that for movie night. But anyway.
Well, I also haven't had any beers, so that helps on being a little more put together.
It may have been inappropriate for me to prompt you to repeat that, but it's happy to hear it, and obviously we'll wish you luck, Chief.
I appreciate it. I'm really hoping I get this one. It'd be so much fun. It's just offer of a lifetime.
Absolutely. Do not kick the ice wall. Do not.
Oh, go ahead.
Do not kick the ice wall.
Don't worry, if it's flat, I'm just going to get sucked right back to North America where the gravity is stabilized anyways.
Absolutely. All right. Okay, we're getting to movie night-ish. Back to science.
A little bit. Well, I hope I was able to help kind of pull some of the spectroscopy and space observatories together in this episode. I hope everybody enjoyed. I'm absolutely starving right now. I did not eat lunch today and have been working for quite a while, so this might be a little bit of a short show today. Is there anything anybody would like to ask or toss out there for future episodes? You're more than welcome to, as always.
The grand finale fire night, maybe?
Well, I do have to fix that leak in the burner. I lit half my leg on fire and my hand on fire, so let me get that fixed, and we will definitely still have a final episode where the spectrometer is involved as well, and the burner is functioning properly.
Interestingly, it happens. The next Science Sunday would happen on New Year's Eve, so you could actually time that to be the end fire episode for fireworks.
Interesting.
I'm writing that down, and we will definitely take a look.
All right. So
I'm glad you've.
Go ahead.
I'm glad you've learned many things from the little series here, Emma. That's all I'm trying to do here is help share information and get people excited about going out and discovering new things on their own, running tests, or
debunking flat Earth horse shit.
Oh, that's Friday.
Yep, wrong show. Anyway, Andy, I don't know if I'm allowed to do this or not. Am I allowed to just briefly show off Tesla coil in its infancy? It's not really done yet,
Of course.
Oh, all right, because
homemade experiments are always welcome on the show, from viewers or from our esteemed panel.
Oh, ooh, we're esteemed. Cool. All right. Yes, it's not done yet, and when it is done, it will be a Simple Science episode, but not a Simple Science episode for kids, for obvious reasons. Powered by house
unholy
current
amounts of electricity.
And yeah, we don't want to actually, or at least unsupervised. We'll still make a kick-ass science fair project. Anyway, let me snap it up. So Andy can here's what the fellow looks like now. It's not done. It's not. The coil is the primary coil is 1/4-inch copper tubing. One end is hardwired. The other end is with a clip, so it can be tuned. Primary coil's about 5 winds, I think. Secondary coil, that was the fun one. That is, I think, 2,000 something, somewhere around 2,100 winds of 8 gauge.
Yeah, you definitely could have used a lathe for that.
Yeah, could have. And actually, you know what I could have done? I could have made a jig with some 3/4-inch board and a hand drill to rotate it. People have done that. You see, that would have taken about an hour to make the jig to do the thing, and then another 20 minutes to wind the coil. I figure it was much more time efficient to just wind it by hand. That way the whole thing was done in 6 hours. Anyway, you'll know what is.
How'd your thumbs feel after all that winding?
I just kind of laid the hands down and went to sleep after that. And but there's not one cross. It's close wound. No coil goes over another. So that was all I asked for. I'm happy that it came out that way. What's missing? The one thing I couldn't make at home is the aluminum toroid for the top to be the top load. So you'll note that little screw on the top just waiting for that toroid to arrive. And the insulator at the top that you can see the screws protruding from halfway through looks very sciencey and electrical-y and all that kind of stuff, doesn't it? You know,
bless you.
Would you like to know what it is?
Sure.
It's 4 of those things you put under your piano legs so they don't dig into the carpet.
Oh, nice.
So that'll provide adequate insulation to keep it from arcing down the center of the tube and spoiling my day. So
very awesome.
That's what it looks like now. You'll get to see it do stuff, and then after you see it do stuff, there'll be a video on how to make your own. And this one, I decided I made the solid state one, the one that was the tabletop model was about 4 or 5 inches tall, and it worked, lit up neon tube, fluorescent lights, and all that sort of thing. But I wanted to make one that was in the original Tesla style, which was with the spark gap, generating the high frequency, and just a big capacitor holding the charge to the primary that's released when the charge builds up. And if anyone is into electronics, recognize this as dangerously close to what used to be a radio transmitter. That's really all it was. The Tesla coil was not even Tesla was building it. Was it was a precursor to spark gap radio, but honestly, he was doing it for show. He could. It was anyway. It's the whole thing is basically a radio transmitter. So, anyway, that's it.
Radio transmitter with a heck of a lot more fun involved.
Indeed, indeed. But anyway, yeah. Well, thank you for letting me show off my my thing there.
Absolutely, very nice work on that.
Yeah, I must agree.
Oh,
that's secondary. Oh man, that looks brutal to wind that, but
that must have been
came out great.
Yeah.
Side.
Yeah.
That must have been a female pug to turn all by yourself.
Look at you avoiding harsh language. Very nice. Okay. That was well done.
Well, by the way, we are currently worrying about two sorts of internet issues. I'm just going to say the first one right now, the Adpugalypse, and the second one being potentially brought about on December 14th, the Netpugalypse.
Okay.
Yeah, well, we'll keep our eyes and ears open for now, though. That's politics is generally not what we do on the show, so.
Indeed. Anyway, yeah, that's all I had. And Jesus.
Oh, very nice work. I'm excited to see the results.
Indeed. Well, if I survive the ordeal, you shall. All right. Well,
okay. Well, that's about all I had for the episode. So,
just remember, everyone, echo chambers are bad, bad, bad.
Indeed. Well, I got nothing further, Chief.
Yeah, I think that's all I have.
All right.
Well, thanks for joining us again for Science Sunday, and we will see you next week.
Hopefully.
Indeed. All right. Good night, everyone.
Have a good night, everybody. Thanks for joining.
Sergeant at Arms.